today is about how our instrumentation can help you analyze your biological samples, specifically viscosity, and that there's value to obtain from dilute formulation characterization, and you can use this information to go all the way to predicting how your product can perform. So we have a little lag here on how the slides transition, but give me a second. Okay, so just a quick outline about what we're going to go over today. So just in case you're not fully familiar with viscosity, we're just going to have an overview here. So what is viscosity? How is it defined? Why is it a crucial parameter to measure? So why should you care about it? And then how can we measure the viscosity of your samples? So a little hint, we're interested in talking about some details about the initium with the VROC technology. And because we're interested in talking about these, what they refer to as intrinsic viscosity measurements, which are really just a concentration series of viscosity measurements in the dilute regime, we're going to give some details about that. And so there's going to have to be some background theory here so that you can understand the types of parameters that you can extract, and that these parameters have a physical meaning relating to your sample, so that they're quite informative. And then we're going to talk about the possibility of using the information that we obtain in the dilute regime to extrapolate and make some predictions on higher concentrations closer to therapeutic levels. So, and then in terms of, so that's sort of one analysis that we can do, and then more in terms of predicting product performance, we can use the viscosity and relate it to the injection process. So how can you predict injectability using viscosity measurements? And so we'll talk a little bit about the fluid mechanical theory behind flow through the syringe, and how that we can then develop some relations to predict the injection force using viscosity values and known properties of the syringe and things of that nature. Okay, so first off then, viscosity. What is it? Why do we care? And how can we measure it? So viscosity is just a defined property, and so it's a calculated property. It's not directly measured, which is why a lot of times you have strange artifacts in viscosity measurements, because it's not a direct measurement, it's a calculation, and a lot of conditions have to be satisfied for this calculation to be correct. But viscosity, just a general way to think of it, is that it's going to characterize the resistance that your fluid has to flow. And so to visualize what this would mean, the general way to describe this is to look at a fluid placed between two parallel plates, where the lower plate is held stationary and we're dragging the upper plate at some particular velocity. And there's a particular gap of fluid in between the plates. And viscosity is just defined as the ratio of shear stress to shear rate. Shear stress is just the force that it takes to drag this upper plate at a particular velocity divided by the area of the plate in contact with the fluid. This is defined as shear stress. And the shear rate is the velocity at which you're dragging this plate divided by the gap distance where the fluid fills. So it's a defined ratio that we then calculate. And so this equation here at the bottom, on the bottom right, where we have stress equal to viscosity times shear rate, it's very clear to see that for a given deformation field or shear rate, as your fluid viscosity increases, you're going to generate more stress in the system. So it makes it more clear that it's this parameter that is going to characterize the resistance to flow. So why is viscosity critical for success in formulating and trying to predict product performance? So there's direct value in knowing the viscosity anytime flow of a material is part of either your manufacturing or processing, or it has something to do with your application. So at any time, if you're pumping or injecting a fluid, viscosity is going to have direct value in how those processes play out. And selecting parameters for them. Something that's not thought of quite as often is that rheology, viscosity specifically, is very useful as an investigative tool. And doing these measurements can give you insight into how the individual molecules behave, what are their characteristics, and then also into protein-protein interactions or molecular pair interactions. And both of these will also depend on the formulation components. So what do you also add into your solution medium that's going to modify how the individual molecules behave and how they interact with each other. So it's almost like a forensic tool where you can go in, do some measurements, and get some insight on what's happening in your system. And this is key if you want to formulate with intent rather than just doing something in a very brute force way and randomly. It's going to allow you to work smart rather than hard, which is always a more efficient way to go. So now getting into the how to measure. So the reason that the VROC, or the viscometer rheometer on a chip technology, is ideal for these types of measurements that we're going to talk about later is one of the big reasons is this micron scale dimensions of the flow cell. So this allows you to use small volumes of sample, and so you can conserve your precious active ingredients. And also it's going to, if you need to go to high shear rates, for example, to predict injectability, the small length scale dimensions of the flow cell will make the presence of flow instabilities or turbulence or secondary flows, whatever you want to call it, much less likely to occur. And also the flow through channel design is such that your sample is never exposed to the environment. Unlike a traditional rotational rheometer, say where you have cone and plate or parallel plates, whatever fixture, there's always going to be an interface exposed to the air. And if you have hydrophobic regions on your molecules or anything that would drive it to the interface, you're going to skew your results. So samples in this type of flow geometry are never exposed, they're protected. And the nature of the flow-through cell also allows you to easily repeat samples without reloading. So you can get multiple runs on a single sample and one loading. So it's going to allow you to get very high-quality measurements while protecting your sample from the environment, eliminating any artifacts that could occur due to that, and then also saving your sample by only requiring very small sample volumes. Now the initium, our latest instrument, combines this VROC technology, and it also adds the convenience of an automated sampling system where you can use anywhere from 40 to 96 samples at a time. The minimum sample volume required is only 26 microliters, and because of this flow-through system, you can retrieve samples if you need to. And as with all the VROC technology, we have the rate sweep options and temperature sweep options, and there's very high repeatability with this instrumentation. And so you can get these high-quality measurements that allows you to do the concentration series that we're going to talk about shortly. And it's very simple to handle. It's basically you prepare the samples, you establish and set up your testing protocol, and then you can leave it alone. You can let it run throughout the day and let it run overnight, but it's just basically prepping it, starting it, and letting it go. So it's very, very convenient for doing a large number of samples, which is always required when you want to look at a variety of concentrations. Okay. So the initium capability, it certainly has the capability to do viscosity measurements for the full range of concentration. So what we're looking at here is just the relative concentration, so your solution viscosity relative to the solvent versus the concentration of your macromolecules. And we can see that you can see the very clear distinction at the higher concentration levels in the therapeutic regime. And we can certainly measure the entire concentration regime. But if we want to zoom in here on this lower concentration region and focus on that, we can see that the instrument is also capable of distinguishing samples in this region, which wasn't so obvious on that full-scale plot. But here is, in this case, is. And there's actually a lot of value to be obtained by doing these measurements in the dilute regime, which is what we're going to sort of explain coming up next. Okay, so dilute solution viscometry. We're going to talk a little bit about the theory behind it, and then that's kind of necessary so that we can understand what you're learning about your samples by doing these measurements and applying the theory to extract some of the parameters. So as I mentioned earlier on, a lot of these measurements are often referred to as intrinsic viscosity measurements, and that's one of the parameters that you can extract from this, and so we want to make it clear what that parameter means and what it's telling you about your samples, in addition to some other parameters that we can extract. Okay, so if you think about viscosity as a function of concentration, and first thinking about the very low concentration limit, so infinite, as you go towards infinite dilution or concentration going to zero. What we know then is that at this point in time, our molecules in the flow field are very far separated from each other and will not really interact with any neighbors. So viscosity in this region, any increase in viscosity in this region due to the presence of the molecules is really just due to the physical presence of the individual molecules and relates to the size and shape of these molecules. As we go higher in concentration, but still dilute, then the molecules, due to the fact that there's just so many more of them, the molecular spacing on average is going to decrease, and they're going to see neighboring molecules. And so now how these molecules interact with each other is going to become important, and it's going to contribute to the viscosity as a function of concentration. And so what you can see in the plot is at very low concentrations in this limit of infinite dilution, it appears somewhat linear. And then you start seeing this deviation from linearity. So that's the introduction of these pair interactions, is introducing this deviation from linearity. Okay, so now it's necessary to put some equations up, even if it's kind of painful, just because it makes it a little more clear, I think, what the parameters mean and why they mean what they do. So as we increase the viscosity and as we increase the concentration rather, and this leads to the increase in viscosity, what we're doing is we're adding complexity to the system. And so the way to do that in mathematical form, the way to systematically add the complexity in, is to do what they refer to as a virial expansion. And so this is a common practice in statistical thermodynamics where it's used for viscosity. It's also used for osmotic pressure, if you're familiar with this. But basically what we're doing is adding higher and higher order terms, which is going to introduce these complexities. So if we look at our equations here for the viscosity relative to the solvent value, we first have the zero order term, which is you have nothing there, it's just solvent. And then we introduce the first order term, which is linear in concentration C, or you can also do the expansion in terms of effective hard sphere volume fraction. And there's a reason why I'm showing that you can do both, because it's going to be relevant to the analysis, some additional analysis that you can do later on. And the coefficient in the first order term is this, with the concentration, is the intrinsic viscosity. So if you remember, at the lower concentrations, the molecules or effective spheres are very far separated and they're not interacting with each other, and it's really all about the individual molecule and its characteristics. So the intrinsic viscosity is this first order correction and is really telling you something about the individual molecules. So the first order correction is going to tell you something about, it's going to depend on things like the molecular weight, the intramolecular interactions and how that relates to the structure of the molecule, and then also the impact on the solvent or your solution medium, and whether that causes the molecules to either expand or contract and collapse on themselves. So the first order term, characterized by this coefficient, the intrinsic viscosity, is talking towards the individual molecule features. So when we go up then and add the second order terms, you remember now that higher concentrations, and so this term is proportional to the square of the concentration, or the hard sphere volume fraction, effective hard sphere volume fraction. And now at these concentration levels, the molecules are going to see each other, and so they're going to interact in some way. And so now the parameters that correspond here to this coefficient for the second order term are going to be indicative of how these molecules are interacting with each other. And they can interact in two main ways, one of them being what they refer to as hydrodynamic interactions. So if you remember, we're measuring viscosity, so we're introducing a flow field. And because there's a neighbor close by to any given molecule, the flow field that that molecule experiences is distorted by the presence of the neighbor. And this is what they refer to as a hydrodynamic interaction. You can also have thermodynamic interactions, and these can be repulsive or attractive. And so some common examples of these are electrostatics and charge systems, hydrophobic interactions if you have some heterogeneities along the backbone and there are certain regions along the molecule that are hydrophobic. This can result in attractions. There's the van der Waals attractions, the fluctuating dipoles causing attraction between neighboring molecules. And all of these thermodynamic interactions can be modified by changing your solution medium. So changing pH, changing ionic strength, changing co-solute can either exaggerate or diminish these types of reactions. And so that's one of the values here, is that when you change your solvent composition, you can get an idea of how you're either enhancing or reducing these thermodynamic interactions. And there may be benefits either way depending on what you're trying to achieve. Okay, so thinking of these types of expansions and how can you use these equations to extract the parameters from your data. So what now we're going to just quickly look at an example here of doing an analysis of a concentration series and extracting these parameters, the intrinsic viscosity and some of the pair interaction parameters. So there's a couple different types of expansions people will actually do to analyze their data, and the exact form of the equation depends on the specific expansion and defines the second order coefficient. So the first one and the most common is the Huggins equation and the corresponding coefficient K sub h. And so this is really just the equation we just looked at on the previous slide, just rearranged slightly such that the intercept is what determines the intrinsic viscosity. So I've just sort of simply defined the relative viscosity as the solution divided by the solvent, and then as I mentioned, this is just rearranged to make analysis simple in terms of getting intercept and a slope to corresponding parameters. And this one is just the expansion of the viscosity, but the Kramer equation is done by expanding about the log of this relative viscosity. And in this case, the intercept is still the intrinsic viscosity value, but now you have a different coefficient that comes from the slope of the curve. So if we look at the plot on the left, it's just the data reduced in the two different ways versus concentration, such that you extract in the limit of infinite dilution, or the intercept gives you the intrinsic viscosity, and the slope of the curve is used to calculate the interaction parameters, either the Huggins coefficient or the Kramer constant. The Huggins equation is used more, I believe, for trying to understand and relate this Huggins constant to the actual particle interactions, and there's a lot of theories worked out for the Huggins equation. But we're introducing the Kramer equation as well because it is used in practice, and there's something interesting about it that we'll talk about later in terms of trying to use this to extract to taking the dilute data and the parameters from the dilute data to extract to the higher, more therapeutic level concentrations. So there's one more type of analysis that we can use. So if you remember earlier on, I said that we can do the expansion in terms of either concentration of your molecules or an effective hard sphere size of your molecules. And the reason this is valuable is that if we look at both of these expansions, we realize that the first order terms need to be equal. And so by setting these terms equal, what we do is we are able to establish a relationship between the hydrodynamic radius and a relationship that allows us to calculate the hydrodynamic radius. So when we set these equal, what we know is the effective hard sphere volume fraction is just going to be the volume taken up by the individual molecule times the number of those molecules per sample volume. And then this hydrodynamic volume is related to the hydrodynamic radius. And if we do some rearranging here, we realize that the hydrodynamic radius is going to depend on this intrinsic viscosity that we can get from our data, the molecular weight, which may most likely be known, and then the Avogadro's constant. So it's easy to estimate some sort of hydrodynamic size of the molecules in your solution. And you can make a comparison of this parameter that you calculate to results from dynamic light scattering to get a reality check. And oftentimes dynamic light scattering is not a practical method and can be skewed much very heavily by contaminants and things of that sort, so it's not always ideal to do light scattering on samples, or you may not even have that capability. But if you can do these viscosity measurements, then you can get an estimate for this hydrodynamic size. So just another example of doing this analysis and actually getting the parameters out. So what we're looking at here is this bovine serum albumin in PBS, and our plot just shows the reduction, the two options for reducing the data versus concentration, where we can look at the intercept to get the intrinsic viscosity and the slope values to get the interaction parameters. And so the table just illustrates what we've been able to extract from this data. Intrinsic viscosity, Huggins coefficient, Kramer constant, and we've estimated our hydrodynamic size. And I've stuck at the bottom of the table there some values that were measured in the literature from dynamic light scattering for the BSA and the range that you get. So you can see that it's comparable to what is measured in dynamic light scattering. The variation is likely going to be due to the fact that in the literature sometimes it's not entirely clear all the details of someone's particular formulation. And as we mentioned before, pH, ionic strength, these things are very important to the nature of the molecule in your solvent and are going to shift things a bit. So to make an exact comparison, you'd have to have a sample that is very clearly equivalent. So this is just an example of one particular material and one particular solution. But if you want to look at it and try to pick up trends, our next slide is looking now at bovine gamma globulin, and we're looking at some solution component variations. And how are we going to pick up the variation in our solution with the parameters that we're extracting here? So the left plot is just viscosity versus concentration, and then the right plot is reduced using the Huggins equation, the appropriate reduction for the Huggins equation versus concentration. And we have the gamma globulin formulated in 3 different solution media, one being just 10 millimolar PBS, the other PBS with a co-solute of the bovine serum albumin, and then in PBS with a particular weight fraction of sucrose. And we've been able to extract intrinsic viscosity, use this to estimate the hydrodynamic radius, and then also extract the interaction parameters. And so what I've sort of highlighted here, although looks like there might be a slight shift in size due to these, it's pretty minimal and sort of on the edge of what you would be confident in. But the shift in the Huggins coefficient, characterizing how these molecules are interacting with each other, is a real shift. And if you go from left to right, we're seeing each one jump up by about 25%. So we're able to see that as we change the solvent composition or the solution medium, we see a shift in how these components are going to interact. And this parameter, since it's the prefactor in the expansion for the viscosity, is going to influence how rapidly the viscosity rises with concentration, which is going to be important to the application. So you can use this to guide you as you formulate and see how changing your formulation is going to change how these components are interacting. And I just wanted to point out, so the text here in red at the bottom, that a lot of the theories that we're talking about here are They're well established and well used in the area of synthetic polymers and colloidal dispersions. And over time, they've built up sort of a very clear understanding of how this interaction parameter trends with certain features of the formulation or the molecules or the colloidal particles. And although these types of formulations or theories are applied in the biological systems, they're not well understood yet. But I think it's quite possible that over time, the trends that are basically done for the synthetic world could also emerge in the biological world, and you could have more clear relationships between what you will see in these parameters and what's happening in your formulation. That just takes time and sort of effort in doing the measurements and analysis. Okay, so although the instrumentation is fully capable of measuring at the higher concentrations, if you're sort of pressed for time or are limited by the actual sample that you have and you don't want to do these measurements, we were interested in trying to see if there's some way to use the information we get from the dilute data to predict the behavior at these higher concentrations or the therapeutic concentration levels. So again, we have here the viscosity, relative viscosity as a function of concentration. And we know the therapeutic levels are somewhere in the vicinity, they're sort of at the edge of this plot, somewhere closer towards 200 milligrams per milliliter. Now, if you look at, strictly speaking, the theoretical limit for dilute analysis is given by the product of the intrinsic viscosity times concentration being less than about 0.2. And so what this means is that for most samples, you're limited to looking at a maximum between about 40 and 50 milligrams per milliliter. But is there some way to utilize these parameters in this dilute limit to predict something towards the 200 milligram per milliliter range, is what we were interested in doing for convenience reasons. So what do we know about types of equations that are used, that are applied to protein solutions at higher concentrations? So a semi-empirical model that it's a slightly modified version of what's already used in the world of colloidal dispersions. It's the RheoSense equation. And it's basically saying that the relative viscosity behaves exponentially with this relationship for concentration, where it includes the intrinsic viscosity, which we've already talked about, but then also what they call a crowding factor and a shape parameter. But the general thought behind this equation is that at some point the viscosity is going to go to infinity or diverge when you reach this maximum packing or jamming of the molecules. There's some limit to how much you can physically put into your solution. And this is what they think about is the excluded volume limitation. So each molecule has some volume that it will exclude all other molecules from. And this is what will then cause you to diverge. And we've seen that if we take some of our data, both the gamma globulin and the serum albumin, that this exponential function fits the data rather well up to these high concentration levels. So the plots here are just the relative viscosity as a function of concentration, the data, and then this fit of the RheoSense equation. So this could work for our systems. So now if we want to think about, as I mentioned, we want to see if we can do something with the dilute information and extend it to the higher concentration levels. So one of the features of this equation is that it's, as I mentioned, expecting to diverge when you reach this maximum concentration. So I've sort of redefined some of the parameters here and defined this concentration C star, which is intended to be the maximum concentration and the point at which the viscosity would diverge. Since even at 200 milligrams per milliliter, we're nowhere near infinite viscosity. So we're nowhere near this divergence, and we're nowhere near then this maximum concentration. So is there some simplified version of this equation that we can use because C over C star is small? So one thing that some people seem to do in the literature is to linearize this Ross-Mitten equation, which is what we've done here using a series expansion. And the first equation is this linearized Ross-Mitten equation, and you see that it has a very familiar form. And so I've sort of added also on the slide the Kramer equation because it has the same form, just a different coefficient in the second order term. And so the question is, at concentrations beyond the strict dilute limit of 40 to 50 milligrams per milliliter, could we actually apply the Kramer equation to predict these viscosities, since we're well below the maximum packing? So what we have on the next slide is basically a fit comparison, where we're going to take this form of, you can think of it as either the Kramer equation or the linearized Ross-Mitten equation, and we're going to scale the data for the Kramer equation and plot it versus concentration, and do a fit strictly in the dilute regime, and then also do a fit over the entire concentration regime and see what kind of parameters we can extract and how they can compare. And we have this done for both the gamma globulin and the bovine serum albumin in PBS. And what you can see from the plots is that, so the red data points are just the dilute data points, and then the blue correspond to the extended full concentration regime. Visually, it looks as though the fits are quite similar and comparable. But then we have in the table the parameters that we've extracted from the fits that we've talked about, the intrinsic viscosity, and then K prime will depend on whether you're thinking about the dilute limit, which would make it the Kramer constant, or if you're thinking about something more concentrated, which would be the crowding factor over the shape factor, which comes from the Ross-Mitten equation. So if we look at, for example, the gamma globulin, the top part of the table, and we compare what we're getting, so first for the intrinsic viscosity in the dilute and full case, they're quite comparable. And then the interaction parameters, slightly more different here, but still comparable. And likewise for the bovine serum albumin. The parameters we extract by fitting strictly in the dilute regime versus the full concentration regime are quite similar. So now if we believe that we can use the parameters that we get from this type of fit in the dilute regime and predict something that's occurring in the therapeutic range, well, what does that look like? So the next slide are some examples of this extrapolation using the Kramer fit parameters. And now we just have a mix of samples here. On the left, it's the gamma globulin in the sucrose solution, and then on the right, it's two different bovine serum albumins, one in PBS, one in with an adjusted ionic strength using sodium chloride. And basically what we've done is we've taken this dilute parameter fit and extended it out to compare it to the data that we actually have. So what we see is that in some instances we're overestimating. So in the example of the sucrose solution with the gamma globulin, depending on the exact concentration, we're overestimating a bit, 3 to 11%. On the BSA, we tend to underpredict anywhere from -1 to -15%. So then if we jump to the next slide, what we have is the table that summarizes many of the samples that we've tried to, where we had a measured viscosity value in this higher concentration regime, and that we've then used this means of estimating something from the dilute data. And it's mainly different solutions of the bovine serum albumin and the gamma globulin. And what we see in general is that our variation between the estimated and the measured tends to range from about -15 to +11%. For the most part, we tend to underpredict, with the exception of the gamma globulin solution with the sucrose added, where we tend to overpredict. But in any case, it's a fairly modest error in terms of prediction, and it may be acceptable to you if you're very limited in either time or sample volume such that you don't want to do the higher concentration measurements. Okay, so now we're going to, so that sort of ends the section on talking about the dilute solution viscometry and trying to not only extract meaning from that, but also use those parameters to extrapolate to higher concentrations just for convenience purposes. Now we're going to shift to something more applied. So I had mentioned that, you know, one of the important reasons for measuring viscosity is that you can have situations where it's directly applicable to how you're using your product. And so in this case, we're going to talk about using the viscosity values to predict the injectability. Okay, so just so you can sort of understand how we develop the relationship for injection force and how it relates to viscosity, we'll just quickly go through some fluid mechanics of the flow through a syringe. So at a steady state, as you're injecting, the force that you need to push to move the piston forward is going to be balanced by two forces. One is any friction that's within the system. Mainly this would come from the friction between the piston and the barrel. And then the obvious one would be the resistance of the fluid to the flow, so a viscous force basically opposing it. We're going to assume that the friction force is minimal, and we're going to ignore that moving forward. And so now what we're going to sort of go over is how we're going to sort of show that the dominant resistance due to the viscous force really comes from the flow in the needle, mainly due to the dimensions of the needle. So we want to do just a little background theory to make it clear that because the needle dimensions are so small relative to the rest of the syringe, that flow through here, the resistance through here is really going to dominate. And it allows us to, and the reason that's important is it allows us to simplify the expressions quite substantially. So we break up the syringe into three zones: the barrel, the transition point, and the needle. The zone 1 and zone 2, which are the barrel and the needle, are very clearly just cylinders and easy to understand. Zone 2 is a slight contraction, a little more complicated. So we're not going to go into detail about that one, but I think it'll become clear when we talk about zone 1 and zone 2 that zone 1 and zone 3 rather, that zone 3, the needle zone, is really the driving factor here. So what we have in the table at the bottom are the diameter of the barrel and the length of the barrel, and we're defining the pressure drop across the barrel, and likewise with the needle. And so you can clearly see the large difference in dimensions that exist between the barrel and the needle, which is going to be the important factor. So sort of focusing in on the pressure gradient that you need in the syringe body and the needle to introduce flow through these cylindrical regions. Basically, for any flow through a circular tube, you're going to have, again, another force balance here. And so it's going to be the force balance, which is the pressure drop times the cross-sectional area of the cylinder, balanced by basically the viscous stress times the area of basically the entire inside of the tube. And this viscous stress is, as we've defined before, the viscosity times the shear rate. Now you can have a non-Newtonian situation, but we're just going to focus on Newtonian fluid at this point and assume that our viscosity is independent of shear rate. So again, we're just looking at another force balance. And this has been worked out and is termed the Huggins-Poiseuille flow for a Newtonian liquid. And so what we see is there's a clearly defined way to relate the shear rate to the flow rate that you want, the mass flow rate that you want, and the radius of the cylinder. And then this translates to the pressure drop across that length of cylinder. And what we see is the pressure drop, delta P3, which we had defined as the needle region, over the pressure drop of the barrel zone, is about 5 orders of magnitude higher. So clearly, the pressure drop required to force the fluid through the needle is the dominant resistance to the piston motion. So what we just assume then is that that's the only factor, and we use that in our force balance to determine the force that is required on the piston. So with this estimate, then we can get a simple equation for the force required on the piston that depends only on dimensions of the syringe, so the radius of the piston, the radius of the needle, the length of the needle, and then also the mass flow rate that you desire to inject, and then of course it's proportional to the viscosity. So you can estimate the injection force using things that you know plus the product viscosity. And our table here just shows an example for two different injection rates and a particular viscosity, fluid viscosity, what the estimated injection force would be in newtons as compared to what was reported. And so you can see that it's quite comparable. The estimate is quite comparable to the reported value. And so this is just a practical example of how you can use viscosity to help you develop your products. Okay, so that, just to summarize everything that we've talked about then, viscosity is a very critical parameter to measure because it's going to allow you to intelligently formulate your systems so that you're not doing guesswork. You have some idea of when you change ionic strength or you change pH, how that's going to change the properties of your system and how it's going to change the nature of the molecules. And it's also going to allow you with confidence to predict how your product is going to perform. And that was the intent of the injectability example. The initium allows you to do the type of measurements you need. You can do the full range of concentration measurements, but it's also ideally suited to look and focus in on the dilute range because it has the ability to distinguish those samples. And it has the convenience as well, such that you can set up a large number of samples and walk away and come back and get this data that is so valuable. And finally, because we believe that the understanding doesn't yet fully exist in the rheology of the biomolecules, but it could exist. Our team is very eager to partner with our customers to analyze samples, to do measurements for you, and to do data analysis so that we can advance the interpretation of the rheology of the biological samples. So with that, I will conclude, and then anyone who wants to now unmute and start asking some questions, I welcome any questions you would have.